Hello everyone, my name is Alexander Schlager and I welcome you from sunny Vienna. I'm a junior researcher at the University of Applied Sciences in St. Pölten, Austria, and I'm specialized into virtual and augmented reality. Because of the current circumstances and a lot of Netflix users, our bandwidth is a little limited. So, to avoid connection problems, I've decided to pre-record this presentation. But I will be present at every slide. So, I hope you will enjoy this talk, and if there are any questions, I will be available afterwards. So, yeah, see ya! Der war nicht schlecht. So let's begin by explaining who we are. The Immersive Media Lab and I are part of the Institute for Creative Media Technologies, or short ICMT, at the University of Applied Sciences in St. Pölten. The ICMT conducts human-centered interdisciplinary research on time-based media and interactive technologies. The institute consists of 3 research groups with a team of 30+ researchers, including media computing, media creation, and digital technologies. As part of the ICMT, it was possible to set up an immersive media lab for interdisciplinary projects, for the development of existing knowledge, but also to create new ideas. With this infrastructure, we have the possibility to develop new dimensions of storytelling, which is an essential matter in art, but also see increasing importance in science. Part of IML is the project called Enlightening Patients with Augmented Reality, short EPAR. Now you know a little bit more about us. Let's talk about EPAR and start with the why. Why did we decide to start with this project in the first place? According to the American Journal of Nursing, low health literacy is a well-known issue. 1 out of 5 American adults lack skills to fully understand implications of processes related to their health. Studies have shown that spoken instructions lead to a higher rate of understanding compared to text for adults with lower literacy skills. Multimedia systems have additional positive effects on the patient's educational needs. We combined these beneficial aspects and developed and evaluated the AR prototype EPAR. So this is my approach for this presentation. First, I will talk about the scenario the app is used for. The next point is about the interactive storytelling involved in this project. After that, I will explain the technical developments like creation of the 3D models, interaction design, and the flow control system. Finally, I will describe the evaluation process of the user experience, the interactions, and our findings. So let's begin with the scenario. EPAR is an app to educate patients about strabismus, the procedure of the surgery, and the needed aftercare. And for short, strabismus is a misalignment of the eyes. But wait! Don't we need 3D vision for stereoscopic content used in an AR or VR headset? Yes, but EPAR is an AR app for smartphones, and in this case the output is a 2D image on the display, so persons with strabismus shouldn't have a problem using a smartphone-based AR system. However, this should be confirmed by a follow-up survey with real patients. According to a survey by Kay Dutter from the RWTH Aachen, the benefits of AR in e-learning are better understanding, long-time memory retention, better collaboration, and increased motivation. But in contrast to the benefits, AR could also lead to attention tunneling, challenge the users with usability difficulties, are sometimes hard to integrate in the classroom, and not all people learn the best at the same way. In the medical field, AR has already arrived with several applications mainly directed to trained doctors and medical students. For patient education, there are only a few options available. EPAR also builds on the results of the AR prototype VIPER, what stands for Virtual Patient Education in Radiotherapy, by Alexander Reit, former student at the St. Pölten University of Applied Sciences. Here, the user can place a hologram of the radiotherapy device, which describes the treatment process. The story of EPAR was developed with the help of an expert in our team, Anna-Maria Lienhardt, who has 7 years of experience studying and working with strabismus in a clinical setting. Based on her experience, she identified the main points to convey to users and simplified the process of the surgery to a minimum number of steps, so the viewer would understand the surgery and the methods behind it without being overwhelmed. Okay, but the slide says interactive storytelling, so what is different to classic storytelling? In classic storytelling, you have a linear structure of the story, like the classic 3-act structure that you know from the theater or movies. The first interactive part of EPAR is the freedom of choice, the ability for the user to choose what information he wants to receive and in which order. For this, EPAR is using a spatial menu with corresponding 3D models as menu items. To test those choices, we wrote the script with Twine and created an interactive and clickable storyboard with Adobe XD. Another part is our interaction triangle. We divided the content of each chapter into scenes. At the beginning of each scene, the information is accessible by text and sound. After this initial information, there is a fork in the story, and the user can choose to either click on the screen to trigger an animation, which shows what they heard before, or they can continue to the next scene immediately. The app always allows the user to restart the scene, replay the animation, and listen to the information again. To animate the user to interact with the scene, we developed 3 interaction prompts. So the first measure was to visually highlight the part of the 3D models that are clickable. The second kind of interaction prompt was haptic feedback with vibration in addition to the visual highlight. As the third type of interaction prompt, we implemented the previous 2 types together with an auditory signal which should alarm the viewer to interact. The environment to develop our prototype was mainly in the game engine Unity 3D. The main reason for using Unity was its framework to manage graphical assets like 3D models, to include audio, build user interfaces, and develop interaction through C# code. Unity has also the advantage that we can easily deploy our Android app to iOS so we can reach an even larger audience. The AR system behind EPAR is Google's AR Core. With AR Core, we had the possibility to place digital objects in the real world and view them through the live camera feed. These objects can be anchored to well-trackable places if the surface has enough visual detail. However, our target group personas include people who have never used AR before, so we decided to use a pre-designed target image printed on paper as a marker. This way of positioning objects in AR Core is called augmented images. The position, rotation, and scale of the virtual object is tied to the paper sheet which is handed out to the user. Ideally, the graphics on the sheet should be carefully designed. It should give the user instructions how to get started with the app, while at the same time achieve a high tracking quality which is dependent on the unique visual features of the image. Also a unique feature is the XML flow system. It's like a toolset of text-based building blocks. With these blocks, we could divide our story into acts and divide those acts into sequential scenes. Those scenes can be equipped with different actions like fading objects in or out, create outlines around an object, add a delay between different actions, switch scenes or acts, and add text that should be displayed on the screen. With the help of Microsoft Azure's text-to-speech, we then generated artificial spoken explanations out of the text in the XML file. The advantage here to regular voice recording is that you can fast iterate different versions of the text at low cost. In addition to the methods performed during the evaluation, the app also generates CSV formatted log files which record the user's progress through the application as an additional automated measure for the future. Besides text and audio, we also needed to create 3D content. The early design goal was to be as realistic as possible, but during development, test users mentioned that a stylized look with abstract shapes would feel more comfortable for them and would reduce their anxiety about the surgery. So now you know a bit more about the app, let's talk about the evaluation. In addition to the storytelling concept, a major part was the usability of the prototype. Therefore, a two-stage usability test was developed in a period of 2 months. Based on the research area of this paper, the following 3 main research questions were defined. Which interaction prompts seems comfortable and goal-oriented to the user? What difficulties and obstacles appeared? Does the three-dimensional augmentation of the content add subjective value to the user? Is it clear to the user how interactions with 3D objects modify the story? In the first stage of the evaluation, we tested the effectiveness of the design concepts. The focus was on observing the actions performed by users and measuring the relevant attributes of a usability test, such as usefulness and effectiveness. 6 experts in the subjects AR, UI, and healthcare attended at the test. Representative tasks, such as starting the app and receiving information about strabismus and the surgery, were given. To ensure the whole functionality of the application got tested, the tasks were written down as step-by-step instructions. Additionally, the participants were encouraged to think out loud to get insights on their thought process. The test took place in a lab-like setup. A sit-back session was performed for formative tests, and the qualitative and quantitative data collected came from the verbal protocol documentation. The post-task questionnaire used the standardized system usability scale plus additional questions on the storytelling concept. For the second stage of the evaluation, possible end users were recruited and we defined 3 different user profiles. Users with low technical knowledge, users with good technical knowledge, and finally, users with high technical knowledge. The test group consisted of 18 participants. For the test, the interaction prompts were implemented in the following way. Chapter 1, Visual. Chapter 2, Visual and Haptic. Chapter 3, Visual, Haptic, and Auditive. For every test, we used the same mid-range smartphone, and part of the test was for the user to perform representative tasks such as answering questions through exploring the application, which led through different chapters with different interaction prompts. Every user was administered to all the tasks, but the order changed in each setup of the experiment, so the influence of one interaction prompt to another was counterbalanced. Because this phase focused on testing usability as well as interactive storytelling, the task description was quite open. The participants had the chance to decide on their own how to reach the goal. Furthermore, they were encouraged to think aloud. Every test lasted between 30 and 45 minutes. The qualitative and quantitative data collected in the second evaluation stage came from the verbal protocol documentation, the post-test questionnaire, interview documentation, and the scores from the SUS. So finally, the results. The collection data from both tests was analyzed and the verbal protocol documentation results, as well as those from the post-test questionnaire, were summarized with a focus on the most frequent participants. The first stage results of the expert participants were used to revise the prototype application, and the main tasks identified were to revise the start procedure, main menu, and the appearance of the textual information. This is because 2 out of 6 had difficulties to figure out what image to scan, 4 out of 6 tried to turn the phone or were searching for a burger-style menu, 3 out of 6 were annoyed by repeating explanations of the menu items. The first evaluation reached the SUS score of 67.5. The second stage, with representative end users and different person groups, gave a median SUS score of 80 over all 3 groups. In every single group, the median SUS score was higher than the value of 68. The implemented improvements based on the first stage evaluation proved to have a positive impact on the application. The starting procedure was clear to almost all participants, and the improved menu was recognized as that. For the end, our findings according to the research questions. Question 1. Which interaction prompts seems comfortable and goal-oriented for the user? 14 out of 18 provided the feedback that a visual highlight is sufficient as an interaction prompt. 4 out of 14 mentioned that it would be comfortable if a further textual or spoken sentence like "click on the scalpel to get further information" would be beneficial. The combination of visual and haptic feedback was comfortable to 2 out of 18 users. Other test users mentioned that the vibration was annoying or they thought someone was calling. 2 out of 18 users liked the combination of visual highlights, vibration, and audio interaction prompts. Others felt stressed as well as confused. 2 users also stated they connected the vibration and sound with danger. Question 2. The benefit of the 3D augmentation of the content. The participants provided good feedback. It was noticeable that the participants could repeat and summarize the content quite well, and therefore forms the basis for a well-founded decision for or against a medical examination or therapy. This result is corroborated by the questionnaires values. I think the three-dimensional augmentation of the content is useful, reasonable, and informative, ranging from "I fully agree" to "do not agree at all," with a median value of 4.5 out of 5. I think the use of the application as a complementary tool can lead to a better understanding of the content of a medical consultation, also from "fully agree" to "do not agree at all," with a median value of 5 out of 5. Coming to question 3, whether it is clear to the user how the interaction with the three-dimensional objects modifies the story with following results. Overall, the user states they had a feeling of control over the system and they know how to interact with it, with a median value of 4 out of 5. The conclusion of the observation and the interview is that the users perceived visual highlights as useful, but in some cases they did not notice them. A goal for future improvements is to revise the highlights as the interaction prompt. For example, by making them larger, especially because the users mentioned that this prompt is their favorite and the most useful one. So this is the end of my presentation, and I hope you got some interesting insights in our research project. Like mentioned in the beginning, I will be available for questions.